everyone. This is Math 2265. We are in the middle of chapter 1.2 actually, and I expect to finish that today in this recorded lesson. Also finish 1.3, maybe even get a preview look at 1.4. We'll get through quite a bit of chapter 1 today. So we'll try to do that. Because I record this on Friday, we've had a lot of rain, well over an inch of rain. High's been in the 40s here south of Riverside. Probably even colder where you live, so it's been quite a day. But anyway, here we are to continue with the lesson here, and I'm going to try to get some highlights going from the book here. We kind of looked at histograms last time, and by now you should have your syllabus and everything is kind of under control. You got the web assign going, you got the first couple assignments already. Actually, all of chapter 1 is open already, so you should be able to use that. It opened up at 4 o'clock today, so give that a shot. There's not that many problems, but some of them are more involved, so I encourage you to use a graphing calculator for some calculations. We'll have more comments on that as we go along. But meanwhile, we did talk about histograms to finish up the lecture last time, and this is just a special kind of a bar chart. And so often, relative frequency, akin to percentages, like 35%, can be used along the y-axis. And we took a brief look at the frequency distribution for hits in 9-inning games. And they took several games, about 19,000 baseball games, and found that the most popular number was 8 hits per team, apparently, and there's many as 27. Certainly there's some no-hitters too. But anyway, we looked at that, and here is a histogram. It's not perfectly symmetrical. We have what seems to be a little bit of skew here. It does look almost symmetrical, but there's more of a right tail here. But we'll talk about that later on. They found ways to get various probabilities, as we mentioned before, about a 1.5% chance of a game with at most 2 hits. And of course, at most is maximum. I have some students in my lower level classes that are totally confused by that. At least is much more popular. That's a minimum, but this is a maximum. So 0 and 1 and 2 all added together, all discrete probabilities. And that could be found in between 5 and 10 hits, etc. You can get a big chunk of them, 64%, have games between 5 and 10 hits for each of the teams individually. Okay, and so we can get into various class intervals or classes. These are done by half units, which is different than before. Here they were done by units, which is, more, easy to look at. But sometimes you have data that needs to be refined a little bit further. So they use the less than sign pretty nicely. So for example here, this number is just shy of 29.5. So we know that this interval that I'm circling here with the cursor would not quite include 29.5, but the next one does include 29.5 and stops just shy of 30. So that's what the less than sign means. So there's no ambiguity. 30.0 doesn't fall in this one or this one. It falls in the right-sided interval because it says at least up to, but not quite including 30. They didn't actually print that one down. But anyway, let's take a look at some more examples here. Power companies need information about customer usage to obtain accurate forecasts of demands. Investors from a company determine energy consumption during a particular period. And so we have data ranging from 2.97 all the way to 18.26. Conveniently, they did arrange this data in order. That's convenient. But then they decide to go from 1 to almost 3, 3 to almost 5, all the way up to 17 through almost 19, and get a distribution here. Now, we have to admit that it is somewhat arbitrary as to how the classes would be given, and nearly always they are the same width, although this book does actually talk about what happens when you have varying widths for your intervals. Each of these have an interval length of 2. 3 minus 1 is 2. 11 minus 9 is 2. So all these have widths of 2. And not too surprisingly, the one in the middle, between 9 and almost 11, has 25 in their numbers. And when you divide by the total, did they give us the total? They didn't, but we find out what the total is, divide the 25 into it. And we see it's around 28%. So 0.278, and that's where the peak would be for that 9 to 11 group. There it is, at not quite 30%. So here, notice they did put it in percent. Typically, the consumer would rather see numbers in percentage, but to me, they're virtually identical. Do you want to put the decimal in for your calculator? Would you rather say percent? Conversationally, percent does make sense to a lot of people. So that's really up to you. I used to make a big deal out of it a long time ago. I just don't care anymore, as long as your answers are correct and perhaps rounded correctly, etc. So anyway, they look at proportion of observations less than 9, and they just group the bottom 4 observations and add them up, and to 2 decimal places at least, we got an answer. But notice they did suffer a little bit of round-off error when you only round to 2 decimals. Yeah, it would have been closer to 0.38, but that's just round-off error in action. So anyway, they do say that if we'd like to go less than 10, this is really splitting hairs. I don't anticipate we'd be doing it, but just in case somebody actually happens to do this, you could split that 0.27 in half. They did say that the biggest class was around 0.27, and if they have to go, instead of less than 9, notice what I'm trying to say is we're going to go less than 10. But 10 isn't a natural dividing point. Less than 11 would have been. So what they decide to do is they cut that little bar in half. That's the best they can do. I'm sure it's not totally accurate, but we would have roughly 50.5%. And oh, by the way, they did check their work and found it was 52.2%. Not too bad. So when you have to depend on approximations, you expect 1 or 2% difference. And there are other times that happens to be too. And here's a reasonable rule of thumb. The number of classes, and how many classes do we have? 1, 2, 3, how many bars? 4, 5, 6, 7, 8, 9. 9 classes could be equal to the square root, approximately, the square root of the number of observations. So I don't happen to know what that number was, but we do take the square root, and apparently they came up with 9. But that would be really up to you. You could do, 7 or 8, maybe even 10 or 12, but you don't want to divide it up too finely. It starts to kind of lose its cohesiveness sometimes. Here's a kind of a special topic that I don't plan to participate in, but what if we did have, equal width items? That's perfectly fine. B is perfectly fine, a little bit wider, and you could have picked that. But then what about unequal width intervals? I don't really plan to cover it. This is more of a curiosity to me. And then you get into various strange looking histograms. But sometimes tables are actually arranged this way, 2 to 4, 4 to 6, 6 to 8. But then suddenly 8 to 12. That's a gap of 4, not 2. Here's a gap of 8, and here's a gap of 10. Sometimes, unfortunately, tables are done this way. Open-ended tables based on age can do that too. They'll just say like 70 plus or 90 plus, and they don't feel like tallying the people's ages, say by deciles, decades, or whatever. So here's one that I cannot explain. But if you did have to do a histogram, look how blobby that is. In fact, it gets kind of squished at the end, but notice how wide that bar is and how narrow these bars are. I've never seen this in a book before. I'm aware of it, but I've never really seen this. I'm not going to pursue it. Let's move on in case somebody thinks this is somewhat important. It literally isn't. I'd rather just go for regular histograms. And their shapes are also pretty interesting too. And you can tell a lot at a glance. They say a picture's worth 1,000 words. Same with statistics. So often histograms are unimodal, having a single peak. And it rises to a peak and then declines. We just saw one of those. A bimodal histogram has 2 different peaks. One that always comes to mind, I may have mentioned it, is the difference in time between eruptions, the waiting time. Say you show up at Old Faithful up at Yellowstone National Park and you just missed the eruption. How long do you have to wait? Well, data that I've seen that may be outdated seem to peak out at around an hour and then peak out at 80 minutes. So 60 minutes and 80 minutes had 2 peaks, but 70, surprisingly, was not common at all. So you'd have this bimodal situation. And here we seem to have even more than that because they mentioned the possibility of multimodal. They do mention reasons for this. Say you're traveling between San Luis Obispo and Monterey. There are 2 major routes you can take. You can take the inland route, which is the shortcut, or along the coast, which takes a little bit longer. So most people would fit into those periods, around 2.5 and around 3.5, let's say. So the heights, though, of college students, especially if you blurred the genders and put males together with females, can appear to be multimodal, but they mentioned the fact that 69 inches average height of males as compared to 64, 65 inches for females is considered to be so close that it might be difficult to actually see the 2 modes there, or two peaks, I should say. But I think in almost every case you could see some sort of camelback type of deal. And here we have several. They have used a computer program, and they've found what the curve could look like from this data. And we see there may be even three peaks, three distinct peaks. And this happens to be the players listed on the rosters back in the Super Bowl of 2009. It's a smoothed up, and it's the weights. And we have three different types of positions that have linemen, that's the heavier ones. The linebacker weights are in the middle, and the other players, all the other players, quarterbacks, wide receivers, they don't tend to be quite as heavy, so they're over here. So you've got three peaks here. I didn't even know that. So histogram would be symmetric if the left half basically is a mirror image of the right half, and it doesn't have to be perfect. It just has to look approximately symmetric. But then we have this idea of positively skewed, and here we have positively skewed. Let's go to the example right here. I've always thought of this as, right skew, but positive skew is what this book uses, but I've used right skew most of the time. And the way I remember that is that we have less data on the right. However, a positive skew might be that it's just leaning in towards the left there a little bit, and the skew means the absence of data as far as a memory trick is concerned. So on the positive side, say a number line where negatives are over here and positives are over here, that could be considered a positive skew or right skew. Negative skew is just the reverse of that. A long left tail, sometimes called left skew, but here the absence of the data, the less data is found on the negative side of the number line, say negatives, zero, positives, that kind of thing. And symmetric, of course, and then bimodal, of course, that kind of thing. So even trimodal over here. So those are skewnesses. And yeah, we'll be looking at types of skewness. And sometimes I just ask questions to say, is it skewed or not? And then if you happen to tell me what type it is, even better. Let's move on. And qualitative data. This one is has to do with the end of 1.2. Here we are, and categorical is the same as qualitative data, and you could put data down for a school rating data between A and F. So apparently we get to grade the schools this time instead of them grading us. We get to grade them, and so we see that apparently B is a very popular one, looking at the relative frequency or just the total frequency if you'd rather do that. And F is not very common, only 4% of the time. D only gets 7% of the time. But A and C are close behind the B, I guess. But B is about 36%. And so that's categorical data. But you could also use it for other things like religion and other things, such as what state you're born in, categorical data. Here is what they call a histogram, or could be just a bar chart. Other books say that this is just a bar chart because it isn't quite as official looking as a histogram would be with continuous data. But I'm not going to worry about it. They're just a different type of histogram. And this is just the bars that are not connected. There's going to be a space in between. And we can later talk about a Pareto chart that this reminds me of, but that's another story. So that has to do with the qualitative data, very short and sweet one. So let's go and move on to multivariate data, and they don't have much to say about this at all. So this is a short section. Wow, I wish they were all this short, huh? So multivariate data is generally rather difficult to describe visually, but there are methods to do so. And I'm thinking of like three-dimensional data that computer programs could do a fantastic job with, and you can rotate it. And it becomes very interesting. You not only get a normal curve, you get more of a normal mound if you have three variables. But anyway, we're not going to do too much on that. Now we of course have exercises, but you can look at those at your leisure. I've decided right now not to ask for you to turn them in, but you can certainly work on them for extra work. But right now the WebAssign is collecting that for points for sure. But if you want extra practice for your tests, I recommend looking at some of the odd-numbered problems in your sections. Visual summaries of data for measures of location are excellent tools. And we can talk about that. This is a very short introductory section. Maybe the data is of the form x sub 1, x sub 2 through x sub n. Each xi is a number. You should have seen that type of format before. So we talk about methods for describing the location of a data set. And we'll talk about that right now as we move into the material. So the mean, the median, Even the mode can be talked about, mid-range or other measures of location. And everybody's heard of the mean. I've taught the mean in pre-algebra classes, so I know you've had this. So let's review. We can put in some mathematical notation that some books don't really give, but you're all exposed. So you all have taken some calculus or are currently co-taking calculus along with this. So we're not going to completely shy away from mathematical notation here like we would in a lower level class, or at least we'd reduce it down to size. So the sample mean is called x bar. It's a little tough to read. That's really kind of blurry. I guess I can expand that. Yeah, you can see the bar there, but I can't read the rest of the pages. So let me see if I can get this centered a little bit better so you can read it better. So the sum of the xi's ranging from 1 to n. So you take all of them and add them up. That's the summation sign, of course, the capital sigma. And then divide by n, the total number in your sample. So this is inserting a sample, which is the prevalent one compared to a population. There's a slightly different one for populations, but this is what we usually do. And then your startup disk is almost full, so I don't need to worry about that right now. So if we had such as 125, 131, etc., the average may be 127.3. And so we have a survey here. They've decided to add up all these numbers and got a total of 229. There were 14 observations, so the average of this is 16.36. What are they talking about? It has to do with absorption percentages for the specimens. This is very much an engineering book, so yeah, this could be familiar to you or perhaps not so familiar. This class doesn't have so many engineers in it, but maybe a few. Anyway, we show all the points like on a dot plot, and so they're all little dots corresponding to one that's even could be considered an outlier, 30 something, yeah, 30.5, but the mean is 16.36, and that's what the x bar is showing. Okay, so x is the x bars are absolute. That's a mistake, isn't it? Yeah, no, it is. I can barely see the x bar. Okay, later on, a population mean can be called mu. I don't know if you've seen that before, but it's a Greek letter m, and we could just divide by the capital N population values. Seems to be a natural extension. If you've got the entire population, call it capital N. But essentially, it's the same exact thing, but mu has a little bit more weight. Many of our problems will assume that we have a mu. It's called a point estimate, whatever the mean is. Here, the sample mean, which is more prevalent right now, would be a single point. Later on, we can expand this into a confidence interval. The mean does have one deficiency, one weakness. If you have 9 people that earn $50,000 a year and one, the boss, who is earning $150 a year, the average is now suddenly $60,000. It's like if Bill Gates moved in next door, suddenly the average price of your dwelling would be a lot higher probably, or income, or however you want to do it, because Bill Gates has been known to have a lot of money for quite a while. But anyway, the mean sometimes may not be the best measure of center here, and so the median comes into play for that. And I'm sure you've seen median too. I've taught median in lower level classes many times, and it would be the middle value or the average of the 2 middle values. We even have formulas here. But basically, if it's a small enough situation, you just sort of count into the center. Or if you know what the number is, and playing some classical music in the background here. Here we're talking about Beethoven. Right now I happen to be listening to Mozart. But anyway, halfway between these 2 middle values, you cut it into halves, and the first 6, the last 6, because that's 12. So we actually average these two, and I know it'll be a 66.9. So that'll be the median. It's not exactly on the list. It's sort of a contrived number, but you see the calculation down here. But that would be impervious to outliers such as this one. And this is sort of interesting. I hadn't thought about this, but not too much anyway. Composer's instructions for playing a particular piece. So many notes on the page that you think that every single symphony would come out exactly the same. But oh no, some go fast and some go slow. And here's a sample of 12 recordings of a famous Beethoven symphony, and a stunningly beautiful work, of course. So anyway, yeah, a lot of them tend towards the middle, but the median could be compared to the mean, and I think they did that. The mean was 68.0. So it's off by about a minute or so, and these are in terms of minutes, how long it took to play that particular symphony, I guess. And so they're pretty close, but there are comments we can make if the median and the mean are becoming different, far apart from each other. And they have some stuff that you can skim through here, of course. And if the mean is equal to what they call mu with a tilde on it, which is another way of saying median. This is unique to this book. I have not really used this notation in at least a long, long time. What they're saying here is if the mean and the median are about the same, then we have a symmetric situation. Now, I'm not saying it has to be exactly the same. This one is off by a little bit. Turns out the mean was a little bit less than the median. So I'm sorry, the mean here, 68.0, is greater than the median. So let's take a look at the picture for that. The mean by itself, the mu, is larger here. So that we have a kind of a skew like this. If we were to try to graph this, and especially if you got like a larger sample, it'd be a positive skew, or a right skew, if you wish. But at what point do you say that they're different? Well, there are tests for that kind of thing. And right now you can just pick either one. You could say it's roughly the same, or you could say that it's not. And they're saying it's not because they're being rather picky about it. I think a minute out of, say, 70 minutes isn't that much of a big deal. But sometimes that's in the eye of the beholder, I guess you could say. So let's see about the other measures of location as we go through this rather quickly. Quartiles, percentiles, trim means. Quartiles are actually pretty interesting because we're going to be seeing box plots very soon. And box plots are really dependent on quartiles. Quartiles, to me, are a way of arranging data into, well, as we see, the median cuts the data set in half, but the quartiles cut it into 4 pieces. It takes a median of the first half, a median of the second half to get quarters. And so, Super Bowl right around the corner, yeah, 4 quarters in a football game, 4 quarters in pro basketball games as well. So it's analogous to a sports event where you start at the beginning with the lowest value, you get to the end of the first quarter, the first quartile, the halftime would be the median, you got your third quartile, and then of course the end of the game where the maximum value would be. And we'll have more to say about that as we get into box plots. But quartiles are a fundamental beginning point for that, so that's where we'll spend most of our time. But percentiles, I'm sure you've heard of them. If you've taken any kind of GRE or SAT or ACT type of test, then they have a way of carving it up into percentiles. And you can see where you land. If you're in the 99th percentile, you're ahead of 99% of the people. And if you're in the first percentile, you're not ahead of hardly anybody. So 50th percentile would be right at the mean. And then we also have a trimmed mean, which they use a little bit more in this book than most books. And you can trim off, say, a 10%, which is a pretty typical one. And the reason they have it is it's a compromise between the mean and the median. I know these are hard to read, but the X bar and the X tilde, a tilde like over an N in Spanish. It's a perfect example of a tilde, but they put a tilde over the X here just to mean median. Other books say MED for median. That really doesn't matter to me. But a 10% trim mean does trim off the smallest 10% of the data and the largest 10% of the data. So it's really cutting out 20% of the data, and that's where the compromise is. And as they explain here, I haven't been reading this word for word, the median only really focuses on the 2 middle values, or perhaps just the 1 middle value. So they don't care so much about the outsides. Outliers don't even affect the median, which is the biggest advantage of median. And I should also add that the median is typically used when you have reason to believe that you do not have bell-shaped data. If you do have bell-shaped normal data, then the mean takes over, and it's still the most popular thing used. But the median is also nice to have, especially if you don't know anything about your data, and that's where the median could really come in. Now, trim mean being a compromise of the two, but the thing that I always forget is the 10% trim mean is actually trimmed off twice that much, or 20% of the data. And so they kind of show an example here, and these are perfect multiples of 10, which is nice. So you can trim off out of the total of 20, the bottom 2 get trimmed off, and the upper 2 get trimmed off. So they will be kind of lopped off at the end, and so we wouldn't have to worry about it. But that would be for a trim mean, which I guess they're not going into right now. But anyway, the production of Bidri is a traditional craft of India, and what they're going to do is show the dot plot. So there's a dot plot. I think we did talk about this before a little bit. And so we see that they stack on top of each other. These are rounded to the nearest tenth, so we do have some duplication. 2.6 has been duplicated, 2.7 has been duplicated. So as I circle right down here, those double dots, the most popular one had 4. That would be called a mode. Your book isn't emphasizing mode right now, but 3.6 would be the most popular one. It shows up 4 times. And it turns out that, let's see here, yeah, then they trim off the some of the numbers here, and so anyway, they're saying that you do get slightly different values. But let's see here. The sample mean is 3.65. You just add them all up and divide by 20. The median, you go into the middle, halfway between the 3.3. They've cut it into half very nicely. Between 3.3 and 3.4 is 3.35. The median often will have an extra decimal beyond the data. That's perfectly okay. It just indicates that you couldn't settle on one number to the nearest tenth. Don't round that number. It is really 3.35. But the trimmed mean, that trims off, and I guess, is this, I guess I must have miscounted. There's 26 of these. So they trim off the bottom 2, which means this is a 7.7% trim mean, or if they trim off the bottom 3, you get a little bit of a different number. I think it's 11 point something or another. But anyway, the trimming does naturally eliminate most outliers. Sometimes you don't even seem to need to do it, but anyway, that's what happens. It's sort of a natural trimming device, and it will get rid of outliers without even thinking about it. They do say that if you're going to do the trimming, which is not a super common event, so I should put this in a priority. This is not a high priority, but there is a little homework on this, so I do need to talk about it. Someplace between 5 and 25%. See, if you have a trim mean of 25%, you're throwing half the data away. You'd better have a good reason for that. That's getting close to just taking the median, if you ask me. So wouldn't have the outliers to worry about. It gets rid of all the outliers. Sometimes a 5% trim mean does not get rid of outliers, by the way, if you have enough of them. Anyway, they go through a little detail there. And so you trim off 2 of them, it's 7.7%. You trim off 3 of them, it's 11.5%. And there's even a way of interpolating, but that does seem to be overkill. Your book really pushes the envelope on a few things here that I'm not quite accustomed to seeing. Now, this is an interesting one. It's not difficult. Categorical data and sample proportions. When a data is categorical, so I take a quick look over there, we do have frequency distribution or a relative frequency distribution provides an effective tabular summary of the data. So the idea is to have a category 1 and a category 2. And so we apparently arbitrarily are putting a 1 in category 1 and a 0 in category 2. But anyway, here's some data here for a size of 10, sample size of 10, saying a couple in a row are category 1, then you have a category 2, and some category 1s, etc., etc. And so they find that you can actually find a mean on this, believe it or not. Sometimes categorical data wouldn't make any sense, but if all you have are 2 options, then you could actually get a mean. I don't know how real important this is, but it does make a point that you're 7/10 of the way between 0 and 1, so you could say 0.7, which means you really have 7 ones out of 10, because the 10 is a nice, easy number to deal with, I'll put it that way. But I'm not sure how important this is. I'm just kind of glossing over it here. But we do have 1 for an observation in the category, 0 for the observation not in the category. And so it's just a sequence of 1s and 0s. And so we could continue and have more than 1 category, of course, and then you could get into things. But then you start running into things like averaging zip codes, which doesn't make any sense, or averaging social security numbers, which also doesn't make any sense, because those are really done, I wouldn't say randomly, but they really aren't quantitative, as most data would be with numbers like that. But if you, for example, had a sample of 100 students, revealing that 38 have Macintosh computers, and that's the 1s, and the 0s do not have Macintosh computers, then we have 38 out of 100, or 0.38, as a point estimate of the proportion of all students who have Macs. So, yeah. And yes, is that enough evidence to show that it's at least a third? Well, there are tests for that. We'll talk about that another time, and we can continue with that. So there's some exercises. I guess I can take a quick look at some of these. But it's not for me to work on the exercises, but they have a few things here in this enhanced edition, and you can go through and calculate a few things, and they've got basically some examples of some problems that we just looked at, and you can calculate, means and medians and stuff. We'll definitely ask you to do that in and the WebAssign. And so as you see, it's some pretty typical problems there, as you can pretty much get a handle on right there. Oh yeah, here's one that has 100 plus, and that's going to happen sometimes where they just simply didn't take the time to get the exact number. And that number could be 1,000,000 or it could be 101. Oh, we got two of them there. So this is one that actually is similar to one that shows up on the WebAssign. So if you trim the mean a little bit, then they kind of go away. Use a trim mean on them. And so anyway, but that does make the mean rather difficult to obtain if you don't even have a solid number to take the mean on. You could get a median though. The median would not be affected by that because they get stuck at the back, and the median is focused on the center, heading towards the center. So let's go into the beginning of measures of variability. It actually went a little bit faster than I thought. Reporting a measure of center gives only partial information about a data set or distribution. Several samples or population may have identical measures of center, yet differ from one another in other important ways, such as the variability. And here are some examples. Dot plots of 3 samples with the same mean and median. That's interesting. So they are symmetric for sure, but the extent of the spread is different for all 3 samples. The first sample has the largest amount of variability. Let's take a close look at number 1. Yeah, that looks like what they call a uniform distribution. They're all just equally spaced, 1 dot apiece. The third is the smallest amount. So look how the third one in dark blue is centered a lot more. But the second one is kind of in between. A bunch of them are in the middle, but then we have a couple of these that one could be accused of being an outlier, and that could be accused of being an outlier. So it's just sort of a mixture between number 1 and number 3. But third has the smallest amount of variability, and the first has a lot of variability. So we have to have a way of dealing with this, and we do have ways, and the most common of which I will say is the standard deviation, but we do have others as well. We have an item called the range. I don't know if they're going to talk about the range right now. Typically books start with that. This book doesn't seem to be doing it. But, oh yeah, here we go. I'm sorry, I didn't see that. Here's the range, and it's simply the maximum minus the minimum value. That's all. Very, very easy. Assuming the data is sorted, of course. If it's not, well, I guess you got to do some sorting. But meanwhile, that's a very rough guide as to how the range would be. And you could actually find the range of the data back in the prior example. And you can see it, there's a change. But it really doesn't provide a ton of information. It's just meant to be a rough guide. What we really do want to find, and I'm going to pretty much call it a halt here. I just want to get my foot on the door on the subject. We find the mean, and we find out how far each of those values deviated from the mean. And later on, we'll kind of use the distance formula and come up with this thing called the standard deviation. And that is the most commonly used by far measure of variability. And we'll kind of run through how to do it algebraically. And I reserve the right to ask one question on this on the test, but primarily you'll be using your graphing calculator to do it. I don't want you to waste a lot of time calculating standard deviation, except for perhaps one easy example I just might toss your way on the test, just to see if you can do it. And actually, we have 2 different formulas. This method here that we're just taking a very brief look at is the explanatory way of what's really going on. However, there is a shortcut formula that obscures the details as to what's really going on and just meant to be a faster way to do it. And it was very popular before calculators started taking over, which is back in the Stone Age. But we'll expose you to it. We'll give you a simple example. We'll ask you to do it. Because if I can ask people in my lower level classes to do a standard deviation, I certainly can ask you guys, just to keep you honest. I mean, but yet, most of the time, you will be using the graphing calculator, which I assume you're using. You know, much of the time we'll just give the standard deviation to you anyway. And of course, the larger the standard deviation, the more spread there is. More spread in the data would be. And as I go back to the last one, both the range and the standard deviation would have a lot in common. The standard deviation would be larger, and then a little bit smaller, and a little bit smaller here. Certainly the range. Actually, number 1 and number 2 are tied in the range. Let's take a close look. 70 minus 30 for both cases 1 and 2 yield a range of 40, but they're not the same. So the range would kind of falter at that point. But the range in option number 3 would be around, 58 minus 42, about 16. 16 compared to 40 definitely shows a difference. And we don't have the standard deviations calculated, but I'm quite sure that we'd have the bigger one on top, and then be a little bit less for the second, a little bit less for the third. And primarily these outliers would give a much bigger value to the standard deviation. It has the same weakness as the mean, in that outliers or large or small values, whether they're official outliers or not, would affect the standard deviation and the mean more dramatically than it ought to. So the median has one solid advantage there. But as far as lining it up for the standard deviation or measure of variability, we're going to settle for range and standard deviation. There's also this thing called the variance that we'll mention as well, but I'm not too interested in that. Okay, that'll do it for now. I think I ran about 40 minutes or so, or 35 minutes, whatever it might be. And I don't intend to usually go 75 minutes on these recordings, but I will go a little bit longer usually. This was a kind of a short one, sort of a warm-up. And we'll let you go. And this is meant to replace the lecture for Monday at 4 o'clock. We'll be back live on Wednesday, 4 o'clock, of course. And any questions, please email me, and we'll have our office hours in effect starting Wednesday, so you can come and talk to me live, say before class if you'd like to do that. Okay, we'll send it off to the finish, and we'll talk to you guys later. Stay dry and stay warm.